Today's lecture will be focused on insoluble compounds, writing KSP equations, KSP expressions, and solving several types of KSP problems. As you recall, in our previous lecture, we divided compounds up into three major categories when it came to their solubility. There were soluble substances, where the substance completely dissolved, slightly soluble substances, where most of it would not dissolve, and then insoluble substances where very, very little of it dissolves. We're now going to focus on the insoluble compounds, the ones where very, very little of it dissolves. The one we're going to focus on for the start of our lecture is silver chloride. Silver chloride, as a solid, if we place that into a container of water, what we find is that most of it will not dissolve. We end up with almost all our silver chloride just sitting at the bottom of our container. The issue is that insoluble really means that very, very little of it dissolves. The water does have an attractive force on the chloride ions and the silver ions and is able to get that solid to dissolve just a little bit. So you end up with a silver ion, chloride ion in very, very low concentrations within your water sample. Eventually, your system will reach an equilibrium where a silver ion and a chloride ion will come into contact with one another and precipitate out. And the rate at which that precipitation occurs will equal the rate at which the silver chloride dissolves. So you establish an equilibrium within your container where the rate of dissolving is the same rate as the precipitation. And at that point, the amount of solid isn't going to change in your container, and the concentration of your ions will remain constant as well. If we translate our diagram into a chemical equation, we end up with the chemical equation that's listed at the top of the problem here, or at the top of the page here, excuse me. You have silver chloride in equilibrium with the silver ions and the chloride ions. If we wanted to write a law of mass action, a K expression for this, we would have the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. The issue here is that for insoluble compounds, your reactant is always going to be a solid. And as we know from our equilibrium unit last unit, solid concentrations do not play a role in the calculation of the law of mass action. So ultimately what we end up with is the product of the ions equals our K value. Now we're going to call this K value something different. Up till now, all you've looked at are KEQs. We're now going to start to call this one KSP, the SP standing for solubility product. So we end up with a K expression. KSP is Ag positive times Cl negative in this specific example. Now, once again, experimentally determining these K values, the law of mass action, this information is going to tell us something about the solubility of the substance. The smaller the value, the more the reactant side is favored in this chemical equation. Okay, so it makes logical sense that we're going to see a lot of really, really small values for our KSP values, given the fact that most of the substances we'll look at during this unit are relatively insoluble compounds. Now, the first type of problem that we can give is we can work back and forth between either solving for KSP or solving for the concentrations that are found in the KSP expression. The first type of problem we have is calculating KSP from solubility. So we're going to calculate the KSP of silver chromate if the solubility is 1.3 times 10 to the minus 4th moles per liter. First thing I'm going to do is write an equilibrium equation. So silver chromate, we're going to have Ag and we're going to have CrO4. Silver has a +1 charge in an ionic state. Chromate has a -2 charge. So I need 2 silvers. That's going to be a solid. Okay. We know that this is a relatively insoluble compound because we're at 1.3 times 10 to the minus 4th for our concentration. That is a very, very low value. So we're going to establish an equilibrium between the solid sitting at the bottom of our container and the ions that it would produce. So 2 silver ions and 1 chromate ion, both of which are aqueous. Now, if I wanted to go ahead and write a KSP expression for this, we'd have KSP equals the concentration of the silver ions times the concentration of the chromate ions. Now, the same rule applies for the law of mass action. If you have a coefficient, it becomes your exponent in the KSP expression. So, because we produce 2 silver ions, we need to have a square for our silver concentration. Now, if we were to conduct a mini ice chart here, we're just going to do the change part. We let x equal the change that's going to occur here. In other words, for every one of the silver chromates that dissolves, it's going to produce 1 of the chromate ions, and it's going to produce twice as much of the silver ions. So the idea is we get the silver chromate to dissolve just a little bit in our water sample. We're going to produce, for every one of the silver chromates that dissolves, we're going to produce twice 2 of the silver ions and 1 of the chromate ions. So we have 2x and x. Now, we already know what x is. We're given the solubility. This number right here is our x value. So we can plug these 2 expressions into our KSP equation with the x value and solve for KSP. So we'd have 2 times 1.3 times 10 to the minus 4th, and that has to be squared, times 1.3 times 10 to the minus 4th, and that will equal KSP. We have 2 significant figures, so when I go ahead and do this calculation, I end up with a final answer of 8.8 times 10 to the negative 12th as our KSP value there. KSP, very small number, 10 to the negative 12th, which means this equilibrium favors the reactant side of the equation. That makes logical sense to us. Since it's an insoluble compound, most of our material is going to end up at the bottom of our container of water. The second type of problem, now instead of calculating KSP from solubility, we're going to flip it. We're going to give you the KSP value and ask you to solve for the solubility. Our compound that we're dealing with here is iron 2 sulfide. So iron 2, we've got iron with a 2 plus charge. Sulfide, the root element there is sulfur with a minus 2 charge. So our compound is going to be FeS as a solid. In equilibrium with its iron ions, we have Fe with a 2 positive charge and our sulfur ions with a 2 minus charge. We're now ready to write a KSP expression. Our KSP expression for this problem would be the concentration of the iron 2 ions times the concentration of the sulfide ions. If we let x equal the change, we know for every one of the iron 2 sulfide molecules that dissolves, we're going to increase our iron concentration by x and increase our sulfide concentration by x. So those are the 2 values that we're going to plug into our expression here. We know our KSP, it's given to us in the problem, 6.0 times 10 to the minus 19th, and that's going to equal x times x, or just simply x squared. We know x is going to be a small value because the KSP is small, which means this reaction favors the reactant side, therefore reinforcing for us that iron 2 sulfide is going to be a relatively insoluble compound. When I go ahead and solve this expression for x, we end up with an answer of 7.7 times 10 to the minus 10th moles per liter as our solubility. Now, one of the things you need to pay attention to in this problem and the previous problem is when we give you units of grams per liter instead of moles per liter. We do not have a device in our chemistry lab that allows us to measure moles. We can calculate moles, but we don't have a device to measure moles. Instead, we measure grams of a particular substance and then add that to a liter of water. Therefore, we need to do a quick conversion. Since our units here for X are moles per liter, we need to use the mole map, one-step conversion to go from the center of the mole map out to the left. So we have 7.7 times 10 to the minus 10th moles per liter. We calculate the molecular mass of the iron 2 sulfide, that is 87.911 grams per mole. We're going to multiply that by that value so that moles cancel out, and we get 6.8 times 10 to the minus 8th grams per liter. Once again, a very, very insoluble compound. The analytical balances that we have available in our lab measure to the 4th decimal place. For us to be able to measure this maths, we'd have to go to the 8th and 9th decimal place to be accurate. A very, very, very small amount of iron sulfide per liter of water there.